Stockman mentioned that the color matching functions are a linear transformation away from the cone fundamentals. And in this video, I'm going to take you through the ideas that lead to that statement, in fact, give you a proof of sorts that it's true. To do that, I'll need to develop a notation for representing stimuli using vector and matrix notation, and I'll quickly go through the color matching experiment using the matrix notation and derive the result that the cone fundamentals themselves are obtained as a linear transformation of color matching functions. So let's start by thinking about vector representation of a color stimulus. So, as we know from Newton, as Andrew mentioned, we can think of light as a spectrum that tells us the amount of power in the light as a function of wavelength, with characteristic colors under neutral viewing of different wavelengths seen monochromatically. And so here's just a spectrum, some arbitrary spectrum plotted as a function of wavelength. And in practice, we always use some instrument that gives us measurements at discrete sample wavelengths. We don't have it as a continuous function. So each of these points shows the power at a sample wavelength. Here, a 10 nanometer sampling between 400 and 700 nanometers. Now, if we think of those discrete samples as just a list of numbers, we can represent them using a vector. So here's a column vector, which I've labeled B, that represents a spectrum. And each of the power that's measured in whatever units it is in can be represented as a number. And so if I have 10 nanometer sampling between 400 and 700 nanometers, I would have 31 samples. And I could call those samples of power B1, B2, all the way up to B31, and I could just stack them up as entries of a vector. And for this this purpose so far, the vector can just be thought of as a list of numbers. The particular wavelength sampling that we use isn't critical to any of this. Any sampling will be discrete. It would just change the length or dimension of the vectors that we're using to represent the samples. Now, once we have samples represented as vectors, we can think of physical operations that we can perform on lights and consider how they're represented in the vector notation using matrix algebra. So, for example, one thing we can do with a light is to reduce its intensity equally at all wavelengths. We could do that physically by putting a perfect ideal neutral density filter in front of the light. And so if we started with some spectrum B1 here and had it at each wavelength as a little vector, and then we have that power at every wavelength with a neutral density filter, taking something that was lighter and making it darker, then we could represent that mathematically by just multiplying the vector times a scalar. So here we have this vector that represents B1, and if we put 0.5, which we can think of as a kind of one-dimensional column vector on the right, then B1 times 0.5 just scales all the entries in this vector to produce the output vector. And so scalar multiplication by a vector represents the physical operation of changing the intensity of a light. Something else that Andrew mentioned in his lecture this morning was color mixing, and he showed you various examples of using a diagram something like this, where we had two lights and we mixed them, we could produce a third light. And the way that happens physically, it's superposition that we're doing physically. And so if we had spectra B1, which is the one that we've been working with, and B2, which is some other spectrum here, and we superimposed them, at each wavelength, the power we got would be the sum of the powers in each alone. And that's the way superposition works. So light mixture is additive in that sense. And we could represent that using the vector and matrix notation as well. Here we have the spectrum B1, and here we have the spectrum B2, and adding two vectors, that operation is just adding them entry by entry pairwise, so that the spectrum B that we got coming out of the superposition here is just the vector sum of the spectral representations of B1 and B2. All right, so those are some operations we can represent using matrix operations on spectral representations. Another thing I just want to have in our back pocket is the idea of monochromatic lights, which are special and which get used when we think about color matching functions. So monochromatic lights, in an idealized sense, have power at only one wavelength. Of course, any real monochromatic light is just an approximation of that. And so we could have a monochromatic light at 440 nanometers, which would just have power here, unit power at the 440 nanometer sample. Here we've got 510, and here we've got 680. Each of these are monochromatic lights, and we can represent those as vectors as well. they've got unit power and we had a monochromatic light, all the entries of the vector that represented that spectrum would be 0 except for one of them, which would be 1. And those of you familiar with linear algebra recognize this as a unit vector in this case 31-dimensional space. So the monochromatic lights are like the unit vectors in a spectral representation, a spectral space, a spectral vector space that represents lights. Great. Now, this seems almost trivial, but it's worth working out. If we have some spectrum, let's say a spectrum with 10 units of power at 423 at 410, all the way down to 3 units of power at 700 nanometers in the 31-dimensional spectral space we're using here in this lecture, we can decompose that into a weighted sum of the basis vectors represented by monochromatic light. So this spectrum here is 10 times the unit vector for 400 nanometer light, the 400 nanometer monochromatic basis vector, 23 times the 410 version, all the way up till 3 times the 700 version. So we've analyzed or decomposed this spectrum here as a sum of the monochromatic lights, where each one, or a superposition of the monochromatic lights physically, where each one has been scaled in intensity corresponding to the power in the original light. Okay, so those are some basic facts about how we can represent lights using vectors. Given that, let's now come back and think a little bit about trichromacy, which again you heard about this morning. And I think, as Andrew mentioned, display devices often act to mix lights. And here's some close-up pictures of some old cathode ray tube devices, one with just circles and one with little bars. This is a Sony Trinitron that represent or can mix 3 primaries. And here is a representation of spectra for the red, green, and blue primaries were typical when I was a student, when the displays we used were mostly cathode ray tube devices, where you had a red phosphor that had rather spiky narrowband or a mixture of narrowband spectra, and green and blue phosphors that were more broadband. And so these would be 3 primary lights, if you will, that are used to make mixtures of 3 lights when you have displays. And we could represent those, if we wanted to, as vectors. In any case, these are 3 primary lights. And again, which primary lights you use in a color matching experiment is somewhat arbitrary. You could use monochromatic lights, you could use mixtures of lights on displays, or lights of other sorts. And as Andrew said, in the color matching experiment, we take a test light, which really can be any arbitrary light here, and we can think of it as being matched by a mixture of the 3 primaries. And indeed, the fundamental result of behavioral color mixing or behavioral color matching is that any test light can be matched by a mixture of 3 independent primaries, as long as you can scale the primaries in intensity, and as long as you can bring one of them over to the other side and mix it with the test as needed, in which case we consider it to have a negative value in its scaling. That's an empirical fact about human color vision that's been verified numerous times and holds to very good approximation. So when we think about what we're doing when we do a color matching experiment, is we're scaling each of 3 primaries by that scalar multiplication method, and then we're superimposing them, which we represent as adding them up. Here I'm not showing the vectors, but I'm showing the spectra, and we get something out, which in this case for the mixture of these 3s would be a spectrum that looks like this. And if we actually consider then what happens in the color matching experiment, if we took some light, a test light like this, and we matched it, we'd get a match that was physically different. In this case, would have the characteristic shape of the mixtures of the 3 primaries that I showed you as a function of wavelength, and it would appear the same to a human observer. And that's the color matching result. And just to summarize all that, again, this is probably familiar given what we talked about this morning and things you know. Behavioral trichromacy we can state as humans with normal color vision, any test light can be matched by a mixture of 3 primaries with a little asterisk for the fine print. It's also true that if only 2 primaries are available, some lights can't be matched. If there are 4 or more primaries available, the matches will not be unique. And the fine print is that the test light can't be too intense relative to the maximum intensities you can obtain with your primaries. We need the convention for negative light, which means that we're bringing that primary over to the other side. And the 3 primaries must be independent from each other, which means that you can't match one of them with a mixture of the other two. So we can think of that color matching experiment, if we want to get quantitative, as a system, an experimental system or an empirical system that takes test lights in. These are controlled by the experimenter. The experimenter sets a mixture of three primaries, which I'm just going to represent here as the columns of a matrix, which I'll refer to as P. So the spectrum of each of the primaries, let's say at its maximum intensity, is a column vector here, and I have that one that might be red, green, and blue. So each column of this matrix is can be thought of as a spectrum, and we just stack them together there in a matrix. And then what we've said is that if we adjust the intensities of each of the three primaries correctly relative to their maximum value, so here I've put in hypothetically 0.25, 0.75, and 0.5, it's scaling the red primary by 0.25, the green by 0.75, and the blue by 0.5, and then mixing them. If that's what the subject sets, and the subject is sort of the controller of the output of this measurement system, then these three numbers here are the match or the tristimulus values relative to this primary, because they appear identical to the subject even though they aren't physically the same. I want to observe here, and this is where matrix algebra and linear algebra start to give us some power, that although I've just stacked these things up here and you might not think they had any particular meaning, matrix multiplication into the tristimulus values, if I take and actually do this operation in MATLAB, where the tristimulus values are in a column vector and I have three columns, one with each of the primaries, what matrix operation multiplication be thought of is taking the first number here, scaling the first column by that, taking the second number, scaling the second column by that, taking the third number and scaling the third column by that, and then adding up the results. This matrix product here, which would be P times the tristimulus values T, actually produces for me the matrix vector representation of the stimulus that's metameric to this light B. But in any case, we'll come back to that fact later because we'll want it as part of showing how it is that the cone fundamentals are a linear transformation of the color matching functions. But first we have to say what the color matching functions are. So if we have a spectrum B and this color matching system, by the virtue of the subject turning the knobs, gives us tristimulus values T in a little 3 vector where we've just stacked them up. We're not going to worry here about experimental error, which obviously you'd have to worry about in practice. Then what we have is that this is a system that takes in spectra and gives us tristimulus values. And what we'd like to say we understood that system is if I handed you the spectrum, you could tell me the tristimulus values without my having to go and do the experiment. Then I'd have it under control and well modeled. So how do we go about doing that? Well, there's an important property of this color matching system, this color matching experiment, which was first noted and credited to Grossman, which is the linearity of this experiment. So let's suppose we have a test light, and we'll call it B1, and it's matched by a mixture of the primaries whose weights are T1, whatever that is, three tristimulus values. And we have some other test light, any other test light, and it has tristimulus values T2. And this arrow just means result of the color matching experiment. When I put this test light in with the primary matrix, the primaries I've chosen sort of set and specified on the side. So B1 goes to T1 and B2 goes to T2. Then Grassmann's laws tell us that if I take any other test light, which is represented as a scaled and superimposed version of these two, so B1 times some scalar plus B2 times some scalar, representing the scaling and superposition, then that will be matched as T1 times W1 plus T2 times W2. That is to say, when I scale and multiply two test lights, the tristimulus values that correspond to it are the same scaled and added tristimulus values. That's the property of a linear system generally. When we have a linear system, it means that matrix algebra can describe its operation. So the advantage of then having this be linear, or a fact that follows, is actually then there's almost a recipe that comes out of linear systems theory that allows us to fully characterize this color matching system. And that goes as follows. Let's imagine now that we can go into the lab and do experiments where we do the color matches and obtain the tristimulus values for each monochromatic test light at whatever wavelength sampling we're using. So we put in a 400 nanometer test light of power 1, and out comes some tri-stimulus values, whatever they are. I've just sort of made these numbers up. And then we do it at 410, and we get some more tri-stimulus values. And then we do it at 420, and we get some more tri-stimulus values, and so forth. We do all 31 of the identity bases for this wavelength sampling, in each case getting out tri-stimulus values. So we've made 31 measurements here, which is a lot in some sense, but it's not all possible measurements that you need to make to characterize color matching. But having done that now, we really can go to town. So that's illustrated by this slide here. Let's imagine we have some arbitrary test light. Now, you could imagine going and putting that test light in and having your subject match it and getting the tri-stimulus values, and that would be one way to find them for an arbitrary test light. But obviously, if we had to do that for every test light you can imagine, we'd be making color matches between now and the next ice age. But another thing we could do is remember, at the beginning, I pointed out that this spectrum here can be represented as the weighted or scaled sum of the identity bases for each monochromatic light. So this thing is 10 times the 400 nanometer representation of the 400 nanometer monochromatic light, 13 times the 410, and so forth off down to 700 nanometers. And this is a scaled sum of test lights. And if we've measured the tri-stimulus values for each of these, 31 measurements that I made or described you can make in the previous slide, then I can predict what would happen when I did this match by taking and scaling those tri-stimulus values by the same scalars required to build up this matrix here, basically swapping in the tri-stimulus values for 400, 410, etc. out to 700. And I've got those because I already measured them, and then scaling each one and then summing them up. That gives me a prediction, which I'll call synthesis, for this tri-stimulus value here that I would have measured. And the linearity of color matching says that when I go this way, which doesn't require any new measurements, I get the same answer as if I had done the actual experiment. So it's that linearity of color matching that then implies that having found the tri-stimulus values for each of the monochromatic lights, I can predict the tri-stimulus values for any arbitrary test light. And we call this CMFs here stands for color matching functions, because what the color matching functions really are the rows that we get, or the set of tri-stimulus values we get, 1, 2, and 3, corresponding to each of the 3 primaries at each of the sample wavelengths. So just to say that again, if I took this vector here and I pop it into the first column of a little matrix, and then I take this vector here and I pop it into the second column, and so forth, popping this last one into this last column, I have a matrix here which I could call big T for tri-stimulus or color matching functions. And that matrix has the feature that this operation I described here is actually performed by matrix multiplication. So remember I told you that this here now is if this here is the original test light, then the effect when I have these lined up in the columns, each of the tri-stimulus values, is to take 10 times the first column plus 13 times the second column and so forth, 21 times the last column, scale them and add them all up. That's exactly the operation I needed here to synthesize the tri-stimulus values to this test light. So if I take this matrix T and I just do a matrix multiply times an arbitrary spectrum, out from me comes the tri-stimulus values corresponding to that. And this matrix T is said to contain, or the rows of it are the color matching functions. And if I use the primaries that corresponded to the XYZ color matching functions, then I'd have the XYZ color matching functions in each of these rows. If I use them corresponding to some other set of primaries, I have the color matching functions for those primaries. So often we don't think of these color matching functions as rows of a matrix, but we can do that, as I've shown you here. Often they're thought of as a plot as a function of wavelengths. So here they are for the Stiles and Birch data, corresponding to some monochromatic primaries. Again, Andrew showed you these earlier with the negative values in some regions. But if we just pick these values here off at a set of sample wavelengths and pop them into the rows of a matrix, we then have the color matching functions in a form where the matrix multiplied by the spectrum can give us directly the tri-stimulus values. So that's really cool because it means that having measured the color matching functions, we now know how to calculate tri-stimulus values for every light, and that depends on the linearity of color matching, or Grassmann's laws. Okay, just to kind of say that again, or come back to one other fact about this. I showed you this diagram before where I represented in the columns of a matrix the spectra of the primaries in the color matching functions. Instead, if I knew the tri-stimulus values, I could take the matrix, multiply here this matrix P times the stimulus values T, and get the spectrum that was metameric to the light B. So we went through that earlier. So I call this metameric spectrum M, and I take this matrix and bring it down here. This, physically, M is the weighted sum of these two columns. So I could write M is equal to the matrix multiply of P times T. Now remember that T itself is this color matching function matrix T times B itself. So if I want to go from a spectrum to its metamer, I just take the primaries that were used in the color matching experiment, the color matching functions themselves, representing them in the two matrices, multiply them together, and then multiply that times the vector representation of B. So just keep this in mind, that P times T times B gives me a metamer for the light B, which is the sum of the primaries here, where T are the color matching functions for those primaries. All right, that tells us about color matching in matrix form. And now let's connect this to the cones, because we'd like to prove that the cone fundamentals are a linear transformation of color matching functions for this matrix T as measured in this way for some primaries, and that it would be true for any primaries. So we'll talk a little bit about now, just remind you of the biological basis of trichromacy, which we again saw this morning. I'll just say it in a slightly different way, which is that if we have some spectrum, it's going to produce excitations in the three classes of cones, the L, M, and S cones. And if we have two different lights and they produce the same excitations in those three classes of cones, then our linking hypothesis between trichromacy as a behavioral observation and trichromacy as a biological observation is that two lights appear the same, or are metamers, when they produce the same excitations in the three, or excitation rates if they're just on steadily, in the three classes of cones, as shown here by just observing that the L cone bar and the L cone bar match, and the M and the M, and the S and the S. It's this biological outcome that we think is the mechanism for the trichromacy that we've talked about before. And Andrew mentioned that we have good estimates now of the cone fundamentals, in large part thanks to his work, which really helped refine those, but that builds on work that goes all the way back, as he mentioned this morning, to Young, Helmholtz, Maxwell, and Koenig in particular, and others who worked since then. So here are the spectra of the three classes of cones, and again, these are functions of wavelength, and I could find their values at each of the discrete wavelengths that I'm using in my vector representation, and I could, if I wanted to, put each of those spectra into the rows of a matrix, which I'm going to call conveniently here R for receptors. And if I want to compute the excitations of the three classes of cones from some corresponding to some spectra, what I need to do for the L cone is to take the sensitivity of the L cone at 400 nanometers and multiply it by the amount of power, and at 410, and multiply it by the amount of power at 410, and 420, and the power at 420. Basically weight the spectra by the sensitivity of the L cones at each wavelength, and then add them all up to get the L cone excitations. And that's what this row of the matrix multiplication does. And there'd be a similar, if I have the M cone sensitivities here, what that again means to have those sensitivities is that if I take the power and I weight the sensitivity at each wavelength by the corresponding power and add them all up, I get the M cone excitations, and same for the S. So this matrix multiplication here, where I take R times the spectrum, gives me the receptor excitations, or the cone excitations, expressed mathematically if I know these receptor sensitivities are. Okay, well now we are on the last slide where we're going to put this all together. So what we've said is that two lights match if they produce the same cone excitation. So if we start with some light B and we multiply it by this matrix R, we'll get a set of cone excitations. And if we have a metamer to that light, and we know it's tri-stimulus coordinates, then the tri-stimulus coordinates times the matrix with the primaries gives me that metamer. I did that a few slides ago and said, let's remember it. But just so you can remember it, I'm going to zip back. There it is. The metamer is equal to P times T where P is this matrix, T is the tristimulus values. So I've got R times P times T, that's the metamer, and R times B have to give me the cone excitations if my theory of color matching is correct and two lights match if they produce the same cone excitation rates. But I have one more fact, which again I asked you to remember before, which that T itself is this color matching function matrix times B. So I can substitute in here for T, T times B, and again, just to remind you, there it is there. I'm plopping in T times B for P, which we had derived even earlier in the lecture. So now I have this equation that says the cone excitations, which I get as R times B, also have to be equal to R times P times T times B. And this has to hold for any choice of vector B I put in here, because this is a general statement that we've derived above for the tristimulus coordinates and the receptor response excitations for any spectrum. So although it's a little tricky to go through this, you need a little more linear algebra. This equation holds for any light B, for any choice here B I put in, then it has to be the case that R right there, R times B, has to be equal to R times P times T times B. If it's true for both of them, then I can just get rid of the B's and write that I've derived this receptor sensitivities R is equal to R times P times T, the color matching functions. And here I've just grouped them together. This is a 3 by n wavelengths matrix, and this is a matrix that's n wavelengths by 3. When I do that matrix multiplication, I get a 3 by 3 matrix. So the receptor sensitivities are obtained as a 3 by 3 matrix multiplication times the matrix representation of the color matching functions. And that really is the definition of what it means for the receptor excitations to be a linear transformation away from the color matching functions. This, of course, was derived for some particular choice of primaries, but the whole derivation was general. So color matching functions I obtain with any set of primaries are going to be a linear transformation away from the cone fundamentals. And the only thing that differs in each case, because obviously the primaries come in here, is what that linear transformation is. And again, Andrew described using measurements of flicker photometry and dichromats to help determine what that matrix was, so he could start with a set of very carefully measured color matching functions and use those to help derive precise estimates of the cone fundamentals. As an aside, I'll say that exactly the same logic, you can do the same derivation to prove that any two sets of color matching functions obtained with different primaries are going to be linear transformations away from each other. And indeed, if you know the two sets of primaries, you can actually say exactly what that linear transformation will be. But that is a derivation for another day, and I will stop the recording here.